So this week we are going to talk about chapter 24 in your book. This is about capacitance, dielectrics, and electric energy storage. Today we'll probably talk about capacitance and some electric energy storage, but dielectrics will probably be for the next time. These are our reading assignments, and these are the suggested problems which we'll hopefully solve. So first, capacitors. I think we are familiar with capacitors. We have seen arrangements like this before, and we calculated the electric field. And the idea is we can put these parallel plates, which we called previously, in a circuit, and we can utilize them to store energy via the charges on the parallel plates. So basically, a capacitor is like two parallel plates with some area A separated by a distance D, and it has a certain charge on it. But of course, it doesn't have to have this like specific geometry. You can wrap things around to save some space in this form, and you can engineer more economic forms that will work equally well. Okay. So in a circuit, we show a capacitor with a sign like this. It's like two lines separated by like an empty space. This looks kind of like battery, which is like this. But in the battery case, we have like one smaller than the other. So, and we also sometimes put charge plus or minus, or sometimes we put V. So suppose you connect a parallel plate or like a capacitor like this in a circuit, and you apply a voltage V. And the question is, how much charge can you put on this thing? And this is actually determined by this equation. The amount of charge is proportional to the applied voltage, which makes sense because the more voltage you apply, the more charge you should have. And the proportionality constant C here is called capacitance. Okay. The important thing here is this C does not depend on Q or V, but it is mostly a material property, or the geometry of the capacitor determines what C is. So the unit of capacitance is, you can work your units. So this is coulomb, this is volt, which is joule per coulomb. You can work this out as like some coulomb square joule, or like you can put this in different forms using your dimensional analysis. But we generally call this as farad. It's like coulomb per volt, or this, we call it farad. Okay. Now let's try to calculate this C, and let's just determine what it could be. And for this, I want to consider this simple model we used a lot. It's like a parallel plate. There's like a uniform electric field, and it has some area and some separation D. So we know electric field. So it has two contributions from this plate and this plate. And each one comes with sigma over epsilon 0. Sigma is charge per unit area. And the total electric field is sigma over epsilon naught. Now, if the electric field is known, we can calculate the voltage difference from like minus A to B, E dot dL. But for constant E, it's going to give us E times D, which is the separation. So this is your volt. So you have an expression for Q, and you have an expression for V. We can put this thing in and then calculate what capacitance could be taking. So I say Q is equal to C. Okay, Q is this Q, C is this C, and V is, I just calculated. It's like E times D, but E is equal to sigma over epsilon 0, but sigma is this. So it ends up being an equation like this. And if you can cancel the Q's here, you get a simple formula for capacitance, which is epsilon naught times area divided by the distance. Okay. So let's do some examples and see how this thing works. So this is the first example. This is example 2 from your book. A cylindrical capacitor consists of a cylinder or wire of radius RB So this thing is RB, surrounded by a coaxial cylindrical shell of inner radius RA. The second thing is RA. So both cylinders have a length L, which we assume is much greater than the separation of the cylinders, RA minus RB. So we can neglect the end effect. So we can neglect these ends and think of these things to be like infinitely long. The capacitor is charged by connecting it to a battery so that one cylinder has a charge plus Q, say, let's say the inner one, and the other one has minus Q. And we would like to determine the formula for capacitance. Okay. So I want to remind you, okay, capacitance C was equal to amount of charge per applied voltage. So we need to get V, and for this we need to get E, right? And for this we use Q. Or you can think of this way. Given Q, calculate E, given E, calculate V, and from this, calculate C. So let me do this. E, I think you must remember like electric field of a one-dimensional wire is, I mean, if you don't remember, you can just use your Gauss law, which is really handy, just 1 second. Like it's like what? E dot dA is equal to Q enclosed divided by epsilon naught. So E is constant, take it outside. A is 2 pi r times some length L is equal to Q enclosed is, let's call it some density lambda times L divided by epsilon 0. So from this, E turns out to be 1 over 2 pi epsilon naught lambda divided by R. And I remind you, lambda is equal to charge per total charge per total length. Let's clean this guy. Now V is equal to, let's integrate it from inside to outside. Inside is RB, outside is RA, and the integral is along radial direction like this. And electric field 1 over 2 pi epsilon naught lambda over R. And if you take this integral, you have something like 1 is 1 over 2 pi epsilon naught. Lambda is Q over L, and integral is going to be, okay, log ln R A minus ln RB. Now I look at this and I ask myself, is this positive? Now RA is bigger than RB, right? So this RA is bigger than RB. So this whole thing seems to be negative. So I just convert it to plus. So I say V is equal to 1 over 2 pi epsilon naught Q over L, ln is going to be RA divided by RB. Okay. Now I get this one. Now I can use this formula. C is equal to Q over V, which is equal to Q over this thing. Copy, paste. I can cancel Q's, and I get C is equal to 2 pi epsilon naught times L divided by ln RA divided by RB. Okay. Now let's check if this is correct. Let's actually look at one limit. in which RA goes to RB. So look at RA goes to RB, which means RA is equal to RB times plus some delta R, then ln RB plus delta R divided by RB is equal to, okay, this is ln 1 plus delta R over RB, but for very small delta R over RB, this thing is approximately delta R over RB. Now I can put this guy back in, right? Then C, okay, maybe I can delete this guy and put this way. So C is going to be 2 pi epsilon naught L divided by delta R over R. I can put it RB. Now I watch this. I say this thing is surface times L, or actually this whole thing is area. This whole thing is area. This thing is D. So this actually checks C is epsilon 0 A over D, which is what we found here, okay, which is what it should be. For small separation, it should be exactly like a parallel plate. The way we choose this surface is not arbitrary, right? We are trying to choose a Gaussian surface in which electric field is constant. So if we choose a Gaussian surface like you suggested, like this, electric field is not constant on this thing, right? It's different. Whereas on this thing, I know it is constant because if you have like a one-dimensional wire or like a tube, doesn't matter. If you have something like this, electric field, I know is going to be constant everywhere. But if you choose like a tube, like you said, like this, you see electric field here and here or here, you have some trouble. So you have to find something, some surface in which the electric field is constant. That's how I just write this in one line because I don't have to do any integral. It's just constant. I take it out and I put the total area. Okay, maybe we can do one more example. It's very similar and see. Actually, I have two more examples like this. A spherical capacitor consists of two thin concentric spherical conducting shells. So this is like a shell. This looks like hollow, but I think you get this is like a three-dimensional spherical shell. Inner radius is RB, outer radius is RA, as shown in figure. The inner shell carries a uniformly distributed charge Q, here Q, on its surface, and the outer minus Q. And we would like to determine the capacitance of the two shells. Okay, let's copy this logic. It's exactly the same thing. Copy. So paste. So I'd like to follow this. But first thing I need is, okay, I know charge. I have charge. What is the electric field inside here, right? In this case, I think most of you can tell it, but if you don't know it, you can choose a Gaussian surface, which is also a spherical shell. So here, it was a cylinder. Here is like a spherical shell, right? Maybe I can start writing 1 over 4 pi epsilon naught. Exactly, right? Q over R squared. Thank you. It's exactly like a point charge in the center, which is very nice. And this comes immediately, this follows immediately from Gauss's law. You can just drive it. So Q to E, we got this now. Q to V, we need to calculate V. I think you also know the V probably, but I can calculate it. It doesn't hurt. So it's like some inner is RB, outer is RA, dr 1 over 4 pi epsilon naught Q over R squared, which should be equal to 1 over 4 pi epsilon naught Q. Okay, there's an overall minus here. That minus cancels with the integral 1 over R. There's like RB to RA, and this is equal to Q over 4 pi epsilon naught 1 over RA minus 1 over RB. And now so before applying this form, I ask myself if this is positive, because this formula is only a proportionality, so I better have a positive V. I just manually change the sign if it's negative. I look at this, 1 over RA is smaller than 1 over RB, so I just change the sign. So fix the sign, Q over 4 pi epsilon naught 1 over RB minus 1 over RA, right? Now I have something positive. RA is bigger, RB is small. Okay, good. And now I can use last thing, this formula. So C, maybe I can align these. C is equal to Q over V, and Q, I just copy what I just got here. Copy, paste, and I cancel these guys. And I have something like 4 pi epsilon naught 1 over RB minus 1 over RA. Okay. Now let's first look at this limit. I want to look at the limit in which RB approaches to RA, or we can call RA is equal to RB plus delta R. And in this case, okay, 1 over RB minus 1 over RA is equal to RB minus R, okay, maybe RA minus RB, RA minus RB divided by RA, RB, and this is approximately delta R over RB squared. And if I put this thing will go to 4 pi epsilon naught divided by delta R over RB squared, which is equal to 4 pi epsilon naught RB squared divided by delta R. And again, I can see that this thing is area, this thing is D, so I have the usual form, epsilon naught A over D with checks, okay? Now I have one more limit, so this was a simple limit. Now I want to ask you the other limit. So if you have just single spherical shell, if you just didn't have this guy outside, only the inner guy, what is the capacitance? What is the capacitance of a single charge spherical shell? I think the idea is like I can let this second guy go to infinity, right? I can take this RA, drive it to infinity, then I only have a single shell, and I can do it in this equation or in this equation. If you take RA, go to infinity, that guy goes 0. What you have is something like this. So C shell, let's call it single shell, is going to be equal to epsilon 0 4 pi R, something like that. Okay. So don't panic if somebody asks you what's the capacitance of a single spherical shell or like a blob. Don't be like, oh, where is the other plate? The other plate is at infinity, so you can just write something like this. So I have one more example on this. Let's do that one too. Capacitance of two long parallel wires. Estimate the capacitance per unit length of two very long straight parallel wires, each of radius r, carrying uniform charges plus q minus q, separated by a distance d, which is large compared to r. Okay, d much bigger than r. So the geometry is something like this. Let's call this guy 0. So the radius here is r. There's some, let's call this point, we are interested in x. And the second wire is at d, and it is, edge is like d minus r because its radius is r, okay? So let's copy our logic here. We have to do this every time. Maybe I can copy it from here. Copy, come back here, paste. So we have to do this. So let's calculate first electric field and then V, right? Electric field is easy. There's basically two wires, and electric field here is coming from this wire and this wire. Since this is negative, electric field of this guy is this way. Since this is positive, the electric field of this guy is like this way. So net electric field is to the left. Let me, keep this in my mind, not to forget. But for the magnitude, I can just write 1 over 2 pi epsilon naught. And the charge density is Q over L divided by X. So this is the positive contribution minus Q over L divided by the distance here. I need to calculate this one. So if this thing is X and if this thing is D, this distance is D minus X. D minus X. And that's the total electric field. So from this, I can calculate V. Let me do it. Is equal to minus, let's call it from R to D minus R. So from here all the way to here, this was R, this was D minus R. And the distance is dr, and it's like Q over L divided by 2 pi epsilon naught 1 over X minus 1 over D minus X. Okay, this, I call this R, but this is actually, this should be X, dx, right? We decided to call this thing X. So this integral I can take. So V is equal to minus Q over 2 pi epsilon 0 L. So this is log, and this is D minus R minus ln R minus, so this second one is ln D minus X, and there's an overall minus coming from, okay, this one should be plus, right? Okay, electric field, this one should be plus. They add up. So this one is plus, this one is plus. So this one, this minus actually comes from the integral. And if I put the limits, what is it? R to D minus R, this should be equal to minus ln R plus ln D, okay, D minus D plus R is this guy, D minus R is D minus R, okay. So this is minus ln R plus ln D minus R. So let me clean this mess here. Now what do I have? I have something like Q over 2 pi epsilon naught L ln, there's another 2 ln D minus R minus ln R. Now I might ask myself, is this positive? It's not positive, right? Actually, if I kept the original form, so this one is minus, this one is positive, right? So, or I can say it like V is equal to, okay, cancel these two, Q over pi epsilon 0 L ln R minus, okay, I think this one, I'm trying to convert it to a positive form. It should be something like this, ln D minus R, which is bigger than ln R. R is the small radius, okay? Now I put this into here, C is equal to Q over V, and I just Q over, copy this, paste, and if you do this, these guys gone. It's equal to pi epsilon 0 L divided by what? Divided by ln d minus r divided by r. Okay, but the question is, I think, asking separated by distance, capacitance per unit length. So it's going to be C over L is the capacitance per unit length, and we'd like to also determine. We'd also like to do this approximation. D much bigger than R, then this thing is going to be approximately D over R. So C over L is going to be approximately pi epsilon divided by ln, what is it? D over R. Okay? And that's the final result. So if you have like something like this, like ln d minus r over r, right? And I have ln d over r minus something like 1. But if d is much bigger than r, this thing is much bigger than 1. So you can forget about this one, right? So you have only ln d over r. So let's carry on. So I told you that we use these things in the circuits, and let's see how these capacitors can be used in circuits. And especially if we are using more than one capacitor, we have to decide how we determine the total capacitor of the thing, right? And there are two examples basically. You can connect multiple capacitors in parallel like this. You can see this one is parallel to this one and parallel to this one, or you can connect them in series, one after the other one after the other one. And the question is, what is the net capacitor of this combo? For this, I can start first with this one, and I know if there I have like a Q1 here, I have minus Q1 here, Q2 here, minus Q2 here, Q3 here, minus Q3 here. But the thing I know about parallel connections, if this is V, this is also V, this is also V. So the voltage is the same, and it is equal to the voltage you apply, which is the battery here. V is equal to VAB. Now let's come to this guy without doing any calculation. So if I have Q here, I have minus Q here, but if you look at this thing, this is like a disconnected piece, which should be neutral, so there must be a charge opposite to this minus Q, which should be plus Q, then it's like minus Q, the same logic here, Q and minus Q. And I also need to determine the voltage. If this is V1, this guy is V2, and this guy is V3, right? I can't say anything about them, but I know some of these three things should be equal to this one, right? So let's write these things. So the C equivalent here is total charge divided by voltage. And total charge is in each case like Q1 plus Q2 plus Q3 divided by V. But I know Q1 over V is C1 and Q2 over V is C2 and Q3 over V is C3. So I can write this thing as C1 plus C2 plus C3. Whereas in this one, C equivalent is equal to, I have the charge Q, right? But I don't have the voltage, right? So I have to do something. So for this, I need to think of total charge divided by total voltage. But total voltage is what? Q divided by V1 plus V2 plus V3. But this thing is equal to 1 over V1 over Q, V1 over D, blah, blah. This thing goes like something like 1 over C1, right? Plus, maybe I don't need the parentheses here. Maybe I can use one more line to make it obvious, V1 over Q plus V2 over Q plus V3 over Q, which is equal to, which implies C equivalent to the -1 is equal to, or I think there's a better way to write this, 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over C3. All right? Let's do these two examples and finish it. So this is example 5 from your book. Determine the capacitance of a single capacitor that will have the same effect as the combination shown in figure. And let's take C1 is equal to C2 is equal to C3. Okay, this guy. So first I take this guy and change it with something equivalent. So it's like, let's connect this, something like that. And let this be this guy, and I call this C23, and this one is C1. And I know C23 is equal to C2 plus C3 because they are in parallel. And if I combine these two, 1 over C equivalent is equal to 1 over C23, which is C2 plus C3 plus 1 over C1. Then C equivalent should be equal to what? C1, C2 plus C1, C3. Divide this whole thing with C1 plus C2 plus C3. And if they're all equal, C1 is equal to C2 is equal to C3, you get something like this. What? 2 over 3, I think C. All right? So this is example 5. Now let's think about 6, which is also about this. Determine the charge on each capacitor in figure and voltage across each, assuming C is given and V is given. Okay. So how do we do this? Okay, maybe I can zoom in. If I have charge Q here, right? Or I can do it more carefully. I have Q here minus Q here. I have Q here minus Q here. But if I look carefully, there's like minus 2Q, so there must be 2Q here, and there must be minus 2Q here. And the voltage, C and V are given. So if this is V and this is V, right? So I think this should be 2V because there's like twice as much charge. Then from here, 3 times V, okay, this V plus 2V is equal to 3V should be equal to V battery, which is given to be 4 volt. Then V is equal to 1/3 of V battery, which is equal to 1/3 times 4.0 volt. So basically V1 is equal to, V1 is equal to 2 over 3 times 4.0 volt. V2 and V3 are equal to 1 over 3 times 4.0 volt. So this was the volt. Charge Q, okay, I think I can use C is equal to Q over V. I know C and I know V, then I can calculate Q as, which is equal to C times V, which is equal to, this is 3 times 10 to minus 6 farad times volts is what? Volt is 4.0. This is volt, and this is equal to 1.2 times 10 to minus 5 coulomb. And this is equal to Q2 and Q3. These two guys have the same charge. And Q1 is twice as much. Q1 is equal to 2.4 times 10 to minus 5 coulomb. C1 have 2Q. Can you explain again that part? Yes. So I said, okay, I said these capacitors are C2 is identical to C3. So if this guy is Q and this guy should also be Q, and in the opposite side, there's like minus Q and minus Q. And if you look at this, like this part, it almost looks like this connected chunk, right? This one. This whole thing looks like a disconnected chunk. So if there is like minus Q here, there must be Q here so that the whole thing is neutral. That's why I put 2Q here. And since C's are the same, if charge is Q and corresponding voltage is V, if charge is twice as much, voltage should be also twice as much. So I have one more example. Let's do this. So two capacitors, C1 is equal to 2.2 microfarad and C2 is equal to 1.2 microfarad are connected in parallel to a 24-volt source, like here. After they are charged, they are disconnected from the source and from each other, and then reconnected directly to each other with the plates of opposite sign connected together. So after they are charged, they are disconnected from the source and from each other, and then reconnected with the opposite plates, opposite signs coming together. So there is like a charge cancellation. And our task is to find the charge on each capacitor and the potential across each after the equilibrium is established. So what is known here, right? I know C1 and I know C2 and I know total voltage is V. So if I use this C is equal to Q over V formula, I can find Q1 as C1 times V and Q2 as C2 times V. Okay, now I know the charges. Now they are disconnected and their opposite sides connected together, right? So initially, this guy is Q1, this guy is Q2, and when you flip, there must be a charge cancellation, like I said. The charge on the first one and the charge in the second one should somehow cancel each other, right? So the total charge after the reconnection, so after reconnection, let's call this total charge should be equal to Q1 plus Q2, which is equal to, oh, sorry, Q1 minus, because there's like a minus sign here. This guy is plus, this guy is minus. So let's Q1 minus Q2, which is equal to C1 minus C2 times V. I just plug this in here. Now these guys should share this total charge, right? This total charge should be shared so that they have like Q1 plus Q2. Like on like C1 capacitor, and this one is on C2 capacitor. But when they are reconnected, I know the voltage should be the same, right? When they are reconnected, I know the voltage should be the same. V1, the voltage across the first one, is equal to Q1 divided by C1. Oh, sorry, maybe I should be careful here. C1 is equal to Q1 over, let me call this V prime because this one is different from this V. And then V prime is equal to Q1 divided by C1. And this should be equal to Q2 divided by C2. Because when they are reconnected, these guys are in parallel. Voltage difference here is the same as voltage difference here. But from this, I already found some relation between Q2 and Q1. Q2 is equal to C2 over C1 times Q1. Now I can put this back in here and find an expression for Q1. Like, let's do this. Q total, which is C2 minus C1 times initial voltage, is equal to Q1 plus Q2. I take the Q1 parenthesis. This is 1 plus Q2 is equal to C2 over C1 times 1, right? Then here, okay, this kind of looks like Q. It's not, it's just 1. From here, I think Q1 is found to be C2 minus C1 divided by, actually this is like, I want to write it C1 minus C2, sorry. This is C1 minus C2. This is C1 minus C2 divided by C1 plus C2 times C1 times V. And I can calculate Q2 similarly, it's going to be C1 minus C2 divided by C1 plus C2 times C2 times V. I just use this formula again. And the voltage, I have already expression for V. So V prime is equal to Q over C1, Q1 over C1, which is equal to C1 minus C2 over C1 plus C2 times V. Okay, maybe I can calculate these numbers. So let's put the numbers. Q1 is equal to C1 minus C2, clear, open 2.2 minus 1.2 divided by 2.2 plus 1.2 and multiply this thing with V times V is 24 is equal to 7 point. So okay, V prime is equal to 7.05, maybe 0.6 volt. So Q1 is equal to, I can use this formula, right? C is equal to Q over V. So Q is equal to C times C1 times V prime, which is equal to what? 2.2 times 10 to the minus 6 times 7.06, which is, okay, times 2.2 is equal to 15.5, 15.5 times 10 to the minus 6 coulomb, and Q2 is equal to C2 times V prime. It's like 1.2 times 10 to the minus 6 times 7.6 is equal to, okay, divide this thing by 2.2, multiply it with 1.2, you get 8.4. 8.4 times 10 to the minus 6 coulomb. Okay? But check these numbers. So I don't understand the difference between Q and Q. Can you explain it? Yes. So initially, you charge the capacitors with some initial charge, capital Q. And then you disconnect the battery and you disconnect these capacitors from each other. And then you switch the sides. You switch this side to this side to this side, and reconnect these guys. Then what happens is, like, initially this was Q1, plus Q1 and plus Q2. Now when you switch the sides, it's like plus Q1 and minus Q2. And I said the total charge after, I mean, they reconnected, there will be some charge cancellations here and here. I call it total charge should be equal to Q1 minus Q2. And I said they will share this total charge in between them, right? After the equilibrium is established, first capacitor will have some Q1 amount and the second capacitor will have some Q2 amount, right? That's the difference between this Q and this Q. I think that's it for today. I think I can answer questions, but if you don't have questions, feel free to leave. I'll continue on Thursday.